So thanks everyone. Thanks for inviting me and for inviting this. And more importantly, thanks for pointing out that I missed some of the word "seemed" in my title on the schedule, even though I'm sure I wasn't the only one who noticed. Anyway, right. So this I'll be telling you about joint work with Lucy Bonato, and it's sort of in. I'll also mention some results with Pedro Boveda. So. I want to start with some background that we've been hearing throughout the week. So on Monday, okay, so there was this meeting here and we came to talk about, we had this goal of understanding Galois actions on the automorphisms on the modular spaces by looking at their actions on the fundamental groups. Right. Sort of understanding elements of the absolute Galois group Q, right, by the image of these elements by their actions. So I know where I'm going with this. Here I have an integer, which is the cyclotomic character that Paul was talking about. You heard about this. And here I'm thinking about an element in the free group on two letters, which are top fundamental group. So this is coming from Bailey's function, the Galois group. So our goal is to sort of think about one goal around here, just to think about these Galois actions. And there was a proposal here of Grothendieck to say that we can probably do better if we understand. We look at the actions on the power, on the collection of all of these fundamental groups at once. Right, which he called a Teichmüller tower. So right here. And so what exactly is this thing? Question. What exactly should this object be? This is kind of a good question. So by around, I think I wrote down all the dates, 2000, Hatcher, I'll just Schneps proposed, made note of the fact that if we look at the fundamental groups, the modulus, that these are equivalent to the profiling completions of the mapping class groups of genus G curves with n boundaries. And I'm openly being sloppy about base points and boundaries versus punctures. I will eventually just be talking about that. So they noticed at this point and said, proposed a topological model for this. So let's say, proposed an idea that this Teichmüller tower should consist of first of all, the collection of all of the mapping class groups, and then all morphisms. Homomorphisms gamma from HN, GN, that comes from nice something. Here's the same thing. What I mean by nice. So to explain what I mean by this, well, there's go back to work with Hatcher and Thurston in the 80s. That the mapping class groups, and we saw some of these. For surfaces with n boundaries have a nice presentation. And I'm just going to put dashes for relations here. Where here, AIs. These are game twists around the boundaries. A full twist around, say, alpha 1 and alpha 2 curves here. And the BJ are twists around curves come from a fancy position. This form a Hanks decomposition. Of my so using this idea, and this is sort of in this steps, is that well, we have a map, let's say an inclusion of surfaces here, so HM. Is a nice subsurface inclusion. If I obtain this, well, not necessarily, I guess, sigma HM from by cutting along some finite number of curves in the on curves and right, so I find beta 1 and beta 2, I could, for example, if I cut along beta 2 here, nice subsurface conclusion, and it induces a map, right? Then mapping class groups comes from inclusion.
If your surface becomes disconnected, you just throw away some components.
Yeah, it's just you just take right, so it's a component. But we were trying to look at all possible like conclusions, so it's not like So it's this huge object, right? It's this huge collection of groups, and it's an absolute ton of maps.
Are you sure it's injective? It's always injective?
Oh, no, sorry.
Yeah, the surface, yes, but not the
Yeah, surface, yes, but not, no, it's not an injective. Okay, so, right, what is this? As I said, this is a huge object. What is this tower? And how would you know if this is a good definition? So in this paper and others, so I'll say I'll be focusing on a theorem of from also 2000, which basically says that, well, there exists some cofinite group which contains the absolute Galois group, and I'm calling it NS. So it had a various omegas and gammas. I got confused. And it is a subgroup of the Grothendieck-Teichmüller group. And well, this group acts on this version. Other automorphisms. Okay, so there's some action here that's compatible with the Galois action. So it's a reasonable definition. And I guess I will also say what definition here, okay. We also know outer automorphisms of this genus 0 version of the tower.
So just to probably very naive question. In this case, what does it mean? Inner automorphisms?
So yeah, this means automorphisms modulo those that act by conjugation.
A conjugation on each.
On each. So this is.
Let's say that the Galois action commutes with all of those maps, but it commutes up to inner automorphisms on either end.
Mm-hmm. Yeah, the Galois action commutes with these nice subsurface inclusions and then up to. I don't remember my handwriting well great, so I'm gonna write. I think this is and it says 90 something on here. So I'm going to put 90. Sorry about that. All right.
And then by this union over G, you mean these?
So there's an action on, in particular, sorry, this one is. The way that they show this is sort of an action on each mapping class group, on the outer automorphisms, each mapping class group that is compatible with these. So I mean this whole tower. I mean this like collection.
This particular tower.
Yeah, I mean this collection of all of them.
Okay. So this NS is not the group of isomorphisms that are compatible with these.
No.
Okay.
Well, yes. It's the group of.
It's the automorphism group of the tower.
Automorphism group of the tower. All right. So this is.
Your inclusion. It's actually an isomorphism.
I guess I'll write a comment.
I should say, since I'm making remarks, that this whole idea is really all written down in Grothendieck, which you did mention, but maybe not enough. Like the whole surface inclusion is what he calls the Lego, famous Lego, where you fit pieces together. So he wrote it all in his very informal language, but it's the basic motivation.
So not the Legos that Dan had right here.
Not the real Legos.
Just through erase. All right. So one idea we want to have here, so our idea is that I'd like to understand a bit better what this tower actually is, and see if we can add information to it or understand it as a topological object. So the idea we have here is that this, what I'm writing down, this tower can be modeled by a relatively simple modular operad. I was going to call S for the little hack. And sort of the theorem, our first theorem, is that, well, if you look on the nodes, endomorphisms or automorphisms, but the endomorphisms, the fixed objects. So this is I realize there's going to be some genus zero stuff, so I'll just write the object fixing endomorphisms of this modular operads and profinite groupoids is isomorphic to this group and contained in. Similarly, I'm going to put a little X here. I'll explain what that means in a second. Which sits inside some cyclic version of the operad, but which is actually basically what Dan was talking about earlier. Which I swapped to T. And this, maybe more interestingly, S here, this modular operad is sort of a homotopical approximation to a topological object. So the just tower in a pretty explicit sense, in the way that I mean, in fact, if I take derived maps, here. All right, so applying the classifying space functor to this modular operad and then profinitely completing, you get some topological thing. And this is actually at this point now everything is infinity. And here I am truncating the maps at genus 1. So this is really like a, I guess, operatic or homotopical version of the two-level principle, which is basically saying I'm going to give you something. And has, all of its maps are determined in genus 0 and 1 in a very explicit way. And up to homotopy, this thing is also this group. And this is a pretty nice space that we can actually study. We'll get back to
that statement about derived endomorphisms also true if you remove the subscript? Or is it?
Well, no, not really, because this thing is no longer that's you can do at some point.
Can you repeat what this subscript means?
Oh, so maybe I should put it here. I'm truncating the modular operator less than or equal to 1. Because, so, and the reason this is so profinite completion of spaces is not necessarily product preserving unless the spaces are really nice. And we don't know about the classifying spaces of the mapping class groups along this one, because they need to be good groups in the sense of there. And turns out that's not something people know. It's not necessarily not true, but it turns out you don't actually need it, which is great. Because that's the idea that this whole power would be generated in. Okay. All right. So what is that? So I'm going to introduce a family of groupoids. SGN. And these groupoids are going to have objects. Very specific type of graph. So we saw something like this before. So objects are graphs connected with n legs, in which every vertex has a base. Okay, so something like this, like the legs are the boundary of the graph, or something like this. Okay. And I'm going to impose just a few things that the legs of the graph are labeled. I have that from 0 and -1. Okay, so to find morphisms in this, we do something that we saw a bunch yesterday, which that we're going to assign a surface to the graph, right? So you can do this sort of informally if you don't do it. You can also use the language of fat graphs to make Natalie laugh by watching me try to glue fat graphs together. Oh yeah, sorry. Well, so genus is the number of loops, yeah. And there have been several other versions of this where you sort of label the vertices by a genus tadpoles. This is also fun. Okay, so for morphisms, so a morphism from some G to G prime, it's going to be, well, so each G, I can associate not just a surface, but a surface plus the Pants decomposition. Where I'm associating the boundaries with this to the legs. And each internal edge is going to be a curve of a Pants constant. So then my morphisms, well, these are going to be a subset of boundary preserving diffeomorphisms of an associated surface. And the type of morphisms you can have between graphs, well, right, so I'm fixing my genus. My legs are just going to be diffeomorphisms of the seams. It's changing Pants decomposition. And in fact, you can do a little bit, right. So, and you can do a little bit better than this. So what I'm doing, I'm setting up, I assume that you would hear more about just by abstract and making a guess in the first afternoon, is I'm building up a groupoid that matches like a curve complex. There's the curve complex. And so what you can actually say more about these morphisms. So the morphisms of SGN have a presentation as well. Oh. And categorical compositions. I haven't said anything about operads yet. They're all compositions of sort of elementary morphisms. And so there's the Dane twist on the boundary. There's a half Dane twist around the boundary mark 0. Have to be a little bit careful to define that. And then there are what are called associative and simple moves. So we'll call them A and S. And I should point out, and this is actually a subtle thing, is that there's actually a lot of these, right? There's an infinite number of these. I'm going to choose one, canonical one. And then all other possible choices of associative move will be sort of up to some. And this move here, this is the difference between sort of gluing up your legs pants and shoving your pants down. Like putting them on inside out, right? And again, there's an infinite family of those, but we're going to make a choice. And we're keeping track of the whole family in the data. Why everything ends up being a homotopy. Okay. So in fact, so our little proposition is that these groupoids form a modular operad. So if I write the collection of all G n, meaning here that we have a series of compositions So here I am talking about gluing surfaces together. So on this is a functor, and on objects, this is given by gluing. I take G in here, and G prime in here. When I write G prime, I mean glue leg 0 of G prime to leg I of B. And I also have contraction morphisms. Oh, sorry, and then on morphisms, the functor is inclusion of Dane twists. So I'm trying to capture exactly the nice maps in the tower. Okay. Where here, if I started with some graph G, my new G is blue leg I to leg J. And then this morphism is inclusion of Dane twists, where the two boundaries go to the new, right, there's a new internal edge that's been created, which gives me a new curve and a Pans decomposition. That's what I'm saying. Okay. So, in fact, these can be profiling and restate. So, in fact, we can entry-wise profinitely complete, and then this composition is determined by passing through
Are you profiling completing each group point?
yes,
And what does that exactly mean?
so that means that so I'm not completing the morphism.
Are you just completing the local forms in each object of the group point?
No, not that one. It's I'm actually taking like the pro object. So this is using theorem of Galois about, because our group weight has some finite number of objects, actually quite small, we can profinitely complete, and then this functor is maybe not product preserving, but it's literally an isomorphic. Fine. It's a relatively small thing, and now I can go and check this explicitly. So I'll do a slight detour. I'm just trying to decide which weird technical thing to tell you at this point. So now there's only technical things left. Okay. And I decided to detour into how this works in genus 0. It's actually kind of tricky, and many of you have already seen me give this talk, but I never actually talk about that part. Try to make it exciting for everybody. Right. So how does this work in genus 0? So other statement here. Right, how is this working? So this, if you truncate this modular operad to 0, you get a cyclic operad. So I'll say that avoids the profinite completion as well. And how do you actually see this? So some of you probably noticed that in genus 0, this, what I described, is very similar to the surface operad. It's also Natalie. And although it's sort of a not strictly associative version, we're playing a little with with keeping all the A moves around. And see how it's a cyclic operad. We had this was already mentioned in Dan's talk. You can kind of look at how your pair of pants, their surface, I mean, just like one generating object. You can map this now to the beautiful sphere that I just put here. Into like the top hemisphere of sphere, and to find cyclic action on it. So this is the way that correctly, sort of what we call the N-conformal balls model for the frame disks, or similarly or equivalently, and mentioned, you can also identify it in genus 0 with this channel body. Right. So what's interesting about this is that you can actually, so by sort of thinking about this, I think we can write down what a cyclic means. If you're not familiar with what cyclic, I mean that you need to know what happens if I change. I've sort of implicitly been writing that the edge marked 0 is at the bottom, but this is just a choice, right? I'm allowing all the labeling. So what happens to this half Dane twist if I move 0 to 1? Right? And you can define the what happens there, and maybe I won't write that down explicitly, but it fixes, I'll tell you out loud, it fixes the full Dane twist, fixes a move, our choice, and it acts by some SO3 action on the half Dane twist, but you can always check out. And so there's a theorem, so that if I forget, here. Right, so we have this little hierarchy of objects. So if I forget down to operads, we'll call this U, that U of this thing is what's called parenthesized within this ribbon braid operad. I don't know if there's been parenthesized ribbon, but we have talked about braids, braids. And here, what's actually really interesting is that if you look exactly at what the cyclic operations are by doing this SO3 action, that the surface operad is equivalent to not the left adjoint, but in fact, there's an exceptional right adjoint up from the forgetful functor from cyclic operads to operads. The construction I'm using is in actually the paper from the board mentioned yesterday, and then very generally in the paper of Gabriel John Paul. So this is how we think about this, and then I can say I have an older paper with Pedro Rivera and Well, we showed that in fact our endomorphisms, which takes objects automorphisms, with the parenthesized ribbon braid operad completed GP, and then you played some games with adjoints, and you get and topologically, once you apply classifying spaces, this becomes sort of a cyclic dendroidal set of profiling space. Cyclic dendroidal space. Okay. So
is it wait, no problem.
yeah.
Who it is?
And I wish I knew it existed for like a long time. So it's yeah, so what the right adjoint does is essentially just, if you think about operations as trees with the root label 0, it just adds copies of trees for every possible labeling groups. And then you can induce the cyclic action. Kind of a nice. Okay. Right, so I said I would just restate the theorem and then go back to explaining to you why I actually think this is interesting. So you can play a similar game with a modular case. And again, we have one condition on here, the endomorphisms which fix objects. The truncated version of this modular operad, which is one, is isomorphic group, big profinite group. And topologically, so the truncation is actually not strictly necessary for this part of the theorem, but when you pass the classifying spaces, it is. So I'm thinking into the room, and I probably should pass it. In fact, so there's quite a lot of hard stuff that happens here. Like once we actually take classifying spaces and try to understand this as a geometric object, a topological object. As I said, profinite completion, we don't have this nice zigzag here. The best we can hope for after applying the classifying space functor is that you'll have a weak equivalent, and that's only in very rare cases. They have to be nice homotopically finite spaces, high finite, good fundamental groups. So that's, and we don't know if the mapping class groups are good. It's greater than equal to 1. Well, I guess there's some knowledge of certain ones in genus 2, but I'm not an expert in that. But it doesn't matter. Somehow there's enough information here to capture this whole group. And the model for this is modular version equal space. Which is all joint work with Philip Hackney and Donald Yao. It turned out to be more irritating. All right, so what about, why is this even a good idea? Right. You actually can say a little bit about what this stuff means geometrically. So just mention briefly in Dan's talk, and will be also somewhat brief at the end of mine. So the spaces, these classifying spaces, are related to the Deligne-Mumford compactification of the modularized case genus G curves with n boundaries. So I also actually meant to say that, like, they're chosen. The reason they're constructed very carefully using this sort of half-comparison compass is that, in fact, they're typical approximations of the mapping class groups. So by which I mean these are very small, nice groupoids, and they are homotopy equivalent after classifying mapping class groups. And they're related to and again, so there's a theorem. Maybe Bill Drummond-Cole in genus 0, and not quite the way I'm stating it, but I'm not going to try to pronounce that. Someone can. And in higher genus, by this pair, and not exactly the way I'm going to say it, but you can manipulate what they said into what I would like to say, which says that we have a homotopy pushout of operads and spaces where we're just sort of trivializing, Dan was saying, homotopically trivializing the circle action around the boundary, relating these spaces to GN. And In fact, it's a profinite completion, the left adjoint. So it behaves nicely with respect to homotopy pushouts. Nice enough, right? And so you can extend this. That's silly. And I can put some hats here. And now this is then not a homotopy push out of operads, but of and then I actually have to truncate. So push out of modular single spaces. So what these are kind of like spaces. They are pre-sheaves over a particular graphical category in profinite spaces that satisfy a Siegel condition or like a type of sheafification. Space-like. And so you can in fact say that you have this model and it's well, Galois Q actually variant. Using this fact that we have the opposite Galois group sitting inside of this profinite group, you can see an action part of it. This is very compatible with this push out and non-trivial, at least at the level of homology, non-trivial. But I think I'm not very good at but the level of homology is just a not trivial action. All right. So in other words, we're talking about sort of giving an approximation to what exactly is in the power of fundamental groups of this, at least the compactification of the modular space. And it's actually quite small, right? It's generated by one tree and three ones. Relatively small thing. And the X that I have here is in fact, there are more endomorphisms of the modular operads than is required to get this group. If we put some conditions on them, we get precise groups, otherwise we get something at least included. I don't have a proof at this time that that is actually smaller. There's in fact more endomorphisms here than just the ones required. Right. And I'm
something about this restriction. How frequently you use one and what will happen if you don't?
Yeah. So, if you don't, so at the group level. So if you just look at the modular operad, I just take F and I can using the fact that profinite completion of this nice finite group of product preserving. I'll be all right getting this. There's a restriction on the S move that is sort of required to get this group. We have more available ways to glue. That's what the X is. Anyway, so this is fine. It's when you do the classifying spaces. So here, when I say the truncation here, I mean, I'm just taking the classifying spaces. Well, to the end where are equal to 1. And the reason that I have to put this on, that basically why are simplicial sets or spaces. In the right direction. It's almost certainly not the correct direction, but we'll see. And you complete their product, right? There might be a map here, but it's basically the only relation you have. So if we add the collection that x and y are both pi finite, and that pi 1 of x, pi 1 of y are good. Oops. Then I can finite spaces. Now here, in my case for my classifying space, so pi 1 of b SGN is the mapping class group. And I only know that these are good if the genus is less than 1. So I don't know, in fact, that you can sort of get, you get some pre-sheaf in spaces. Classifying spaces, but it's otherwise somewhat meaningless. They're just a bunch of maps hanging around. But when you calculate, you can actually force the Siegel condition on your modular operads spaces. So you actually have like a nice, well-defined product there. Well-defined up to homotopy, but it's, could be worse. Yeah, so that's what that truncation is about this. Now, I don't know.
You're saying it doesn't matter.
It doesn't matter because it turns out that's enough to get this object. And in fact, there's even at that point, there's still. But I think it's nice. I think that's the point. Yes.
If the goal is to capture the object, then you've done it in genus 1. But if the goal is to capture Galois of Q bar over Q, you have the whole point of the two-level principle of Grothendieck is that if you get up to genus 1, you then automatically extend to all the other mapping class groups in those maps. Even if you can't prove it because of this problem, do you have a conjecture, like a two-level principle in this situation that says like a formulation of that principle in this context?
That this is not something that I would call a modular operad, right? It's just some pre-sheaf over graphs. Then this homotopy push out and profile, this is still good. So you still have this Galois equivariant action on both here and on the Deligne-Mumford compactifications, whatever this means. So at this point, right, this is I'm replacing this with a pre-sheaf over a graphical category, but it's still modeling the moduli space opera. And that works, but it's not sort of it's all I can tell you is it's a pre-sheaf.
And that would you conjecture that the theorem would be true even if you don't truncate at 1, even if conjecture.
I would conjecture that to be true, yes. Up to knowing, up to the fact that this is just some weird thing. But like it interacts well with all the gluing maps. Just that those gluing maps may not be
as opposed to if you don't truncate at 1, would the group be smaller than NS and maybe closer to GQ or something like that?
It's entirely possible because even at truncating at 1, so there are more automorphisms there, or homotopy automorphisms. I just can't prove that they actually at the moment that they actually make the group smaller. There's more there than I need. Strict against this group, but I haven't. It's not clear that they don't degenerate. Like we have some extra relation.
Oh, I see.
NS gives an extra relation, but it's not clear that that relation doesn't
I understand, but but more relations are interesting too.
Yeah, no, exactly. So, yeah, so there is some extra data in these endomorphisms, but and it gives one additional relation on, but I don't know that it's not, I don't know that it's not trivial. Yeah. Yeah.
Well, actually, it's not really a mathematical question. It's vaguely related to your talk because it has to do with finite Grothendieck-Teichmüller theory. But just I prefer to say publicly because it's easier. I'm supposed to give a talk this afternoon. It would be about finite Grothendieck-Teichmüller theory. It would have a very different flavor, but whatever. But the obstacles are first, the weather is much nicer than it was anticipated by the weather forecast. It's vaguely scribbled on the program downstairs without a title. And also it says it's at 4 and I was told it should be at 3:30. So it's up to the organizer. I can give the talk, but at what time?
Sorry, definitely at 4. And it was always at 4.
Is it really 4?
Yes.
But then tea, I mean,
What about cake?
tea and cake.
Yes, it's involved.
So you want tea and cake. And if I talk for 50 minutes.
Tea and cake will be after your talk.
Yeah, but then there will be 10 minutes.
Or 20 minutes we'll manage. And then we'll shift the other talk by 10 minutes. So,
okay, so I am supposed to talk at 4 about.
yeah, so
okay.
That's the answer to the question, right?
Whether it rains or not.
I want to say something a little bit more about how you come up with the morphisms of this groupoid, but I guessed from your abstract that that would be this afternoon. Really helpful. These complex. Yeah.
So I asked you at some point, but have you thought about the Weintraub logarithmic model for this?
I've thought about it in the sense that I realize I don't know enough algebraic geometry to tell you like how the logarithm. I don't understand how the Galois maps work. Model. That would be more data. So yeah, so what you really want, right? We don't want this complication here. Get even closer to what we should be looking for. But I don't know how to. And there is a paper by Weintraub that has a more geometric model of the little disks. Version of this using log geometry. So, yeah, that's a work in progress for me.
Some higher genus.
Yeah, there's in the higher genus as well, but even the genus 0 case I don't play.
Can you say anything about the entire homotopy type of these derived endomorphism spaces? Not just by 0, but the higher homotopy.
Yeah, no, they yes, but
Just a pi 1.
yeah, there's a pi 1, but I don't know what it is.
Okay, maybe let's thank Marcy again.